Hello and welcome to Calculus Tutorial. We are going to be taking a look at antiderivatives some more and what we can do with that plus c, kind of what it means, how can we solve for plus c so it's no longer a number we don't know, and then we're going to apply that to a motion example. So first, what does this plus c sort of mean? So we've got a nice polynomial here. Let's take the antiderivative. So when we take the antiderivative, the x squared will become x cubed. Then we divide by 3, so that's going to cancel out that 3. I'll put it there for now. So that'll be 3 over 3. Plus, this will be 6x squared. But then you have to divide by that 2. Plus 4x plus c. And then if you want to simplify that, make it look a little bit nicer, x cubed plus 3x squared plus 4x plus c. Now, what does that plus c mean? Well, it could be any number. So what we're going to do is we're going to plug some numbers in and graph them and see what it looks like. So first, I'm just going to plug it in with a 0 for c. So x cubed, there we go, x cubed plus 3x squared. Oh, I'm typing that in wrong, aren't I? There we go. Plus 3x squared plus 4x. And I'm going to put plus 0. I guess I don't need to put plus 0. So there's my first graph. You can see I've got a cubic here. And now I'm going to put a few more in. Well, c does not have to be 0. It could be any number. So I'm going to plug in a few more. I'm going to make c equal to 1, equal to 3, equal to 5, maybe a negative in there. I'm going to put a whole bunch of numbers for c, and we're going to take a look at those graphs. Alright, so here you can see I've got a few more equations typed in. I made c equal to 2, 6, negative 3, and 6 as well. So when I graph them, you'll see I have a whole bunch of graphs, but what I'm hoping you notice is that in a way they're all parallel. They never actually touch one another. Yes, they get closer together, but they'll never actually be crossing each other. I want you to focus on that idea of parallel. Why are they parallel? Well, because they have the same derivative, the same slope, which is the definition of parallel. If I take the derivative of this, they all come back to the same answer, 3x squared plus 6x plus 4. No matter what number you put in for c, that will not affect the slope. And so that c value is just moving the graph up or it's moving the graph down. It's not changing the shape, just changing where the graph is. So if we take all these possibilities, and yes, it goes up forever and it goes down forever, but if I tell you one specific point, say right there, and say that graph has to go through that point, well, there's only one graph that will go through that point. It can only be one because they never cross each other. And so if you take one point, there's only one graph that will go through that point. And so that is one way that we can solve for c, is if I tell you one point that the graph goes through, you can then get a number for c. So let me show you how that works here. Oops. Sorry about that. I misclicked a little bit. Trying to hit the eraser. So, let's solve for c now that we can kind of see what that c actually does. So we have our f prime is equal to 2 cosine x plus 1. So if I want to figure out what f is, I need to take the antiderivative. So the antiderivative is going to be 2 sine of x. The the antiderivative of cosine is sine, and it's positive, so we don't add any negative there, plus x plus c. All right, but now I want to get rid of that c. And the way we get rid of it is I have to tell you one more piece of information. I have to give you a point. So if I'm telling you f of pi over 2 is equal to 2, I'm saying this has to go through the point pi over 2, comma 2. You got your x and your y. Well, if we plug that in, we should be able to solve for c. So my y value is 2, so that's going to go in for your y value. Your x value is pi over 2, so that is going to go in for x. Plus another x, pi over 2, plus c. So now we have an equation with only one variable. We can solve this. So let's see, what do we get here? What is sine of pi over 2? Real quick, if you're rusty on your trig, sine looks like this. This is 2 pi. This is pi. So halfway in between is pi over 2, which is 1. So we have 2 times 1, which doesn't change anything, plus pi over 2 plus c is equal to 2. Well, subtract 2 from both sides. Ooh, that goes away. So you're left with 0 on that side. Subtract pi over 2 from both sides as well. And you're left with c is equal to negative pi over 2. So our function f of x, I guess I got room right here, we can now complete it and get rid of the c. 2 sine of x plus x minus pi over 2. You can take the derivative and you will still get back to this, and this function will go through that point. So we've solved for c. All you really do is plug in the point. That's really all there is to it, and you can get rid of c. Alright, that has some pretty important implications for motion problems. So let's take a look at how this can help us with motion problems. So a lead baseball is thrown straight down with a velocity of 10 meters per second from a hot air balloon that is 500 feet in the air. Don't stand next to hot air balloons when you're in calculus class. Just saying. Write an equation that models the height of the lead ball as it falls. So, if we want to model the height, that is position. Now we know it starts at 500 feet up, but that's just where it starts, way up here. So let's think about velocity. We know that we're throwing it at 10 meters per second, but of course it's going to be accelerated by gravity, so we don't really have an equation there either. The only thing that we know for certain here on Earth is that acceleration is always equal to negative 9.8. So we have to start with that. To go from acceleration to velocity, we have to take the antiderivative. I'll put the function notation there. So that means we're going to take the antiderivative of negative 9.8. That is just a constant. So velocity is equal to, velocity is equal to negative 9.8 t, but don't forget the plus c. Well, what's the plus c going to be? Well, to get rid of plus c, I have to plug in what I know. I know that the velocity starts at 10 meters per second. I guess to make sure we have our units right, we are throwing it down, so hopefully it makes sense that that should be negative. It's going down. And so that gives us the point 0, negative 10. At 0 seconds, it's going down at 10 meters per second. Well, if you plug in 0, that goes away, and you're left with negative 10 is equal to c. So our velocity equation will be negative 9.8 t minus 10. Hopefully you can see if you plug in 0, you'll get negative 10. Well, that gets us here. Now we have to go one more time to get to position. So position is going to be the antiderivative of velocity. So we are going to take the antiderivative of negative 9.8 t minus 10. What is that antiderivative? Well, t becomes t squared. Then I have to divide that by 2, which is 4.9. If you are in physics, I'm hoping some of these numbers look familiar to you. This will become minus 10t. But there is another plus c. As always, when you take an antiderivative. Well, what do we know about position? Well, we know at time 0, the position is 500. So when we plug in 0, we better get 500. Well, 0 cancels this out, 0 cancels this out. That means this is left to be 500. So our ending position equation is equal to negative 4.9 t squared minus 10t plus 500. So using the plus c and solving for plus c, we can continue to take the antiderivative and work our way backwards from acceleration all the way to position. Alright, that sort of covers what you can do with the plus c and how to get rid of it and how it can help you with motion problems when you have to work your way through multiple antiderivatives.